So let's officially start, okay? Cameras rolling. All right, welcome to Intro to Statistical Programming, is that what I called it? In the afternoon session of PyCon 2017. Welcome to Portland. I was sitting there this morning in a hipster coffee shop, which I like to frequent where I live too, drinking, a pour-over. Bon Iver was playing in the background. I just felt like I was here. So I'm in Portland, and I'm feeling great. My name is Chris Fonnesbeck. I'm an assistant professor of biostatistics at the Vanderbilt University Medical Center. I'm not an employee of Vanderbilt University. We split. We're a different institution now. So I work on primarily epidemiology, infectious disease, as well as Bayesian statistics, computational statistics, and evidence-based medicine. I'm also a Python developer. And this is my first PyCon, at least the first one that I've spoken at. I've been to lots of SciPys, so you may have seen me there before, but I haven't been to many of these. So first we're going to deal with some logistics. The first is sticky notes. I've got, how many have taken software carpentry before? Anybody? Nobody? Oh, 3 or 4, okay. All right, this is a cool little system that I've picked up for teaching and things like this. You're gonna get 2 sticky notes, and I found star-shaped sticky notes. It's really cool. And each of you will take each of you will take 2, one of each color. When you have an issue, you stick your yellow sticky note. We'll use yellow for problems, like it's nature's warning color, right? Bees and poisonous fish, they're all have yellow on them. So we're going to use that as trouble. And then occasionally I'll say, when you're doing an exercise, put up your blue sticky when you're done. And then I'll know if you're doing an exercise that once we get to kind of 70% done. So each of you will have a blue and a yellow. So just pass these around. Here, let me do half on one side, and half on the other. Did I mention they're star-shaped? Oh, maybe a few more. There we go. Pass those down. Take one of each color and pass it down. Yeah, this tends to work really well rather than... And then if you've got a question during the session of any kind, could be technical or whatever, you can put your yellow sticky up there, and that way you don't have to sit there with your arm up in the air. So that's sticky notes. This session's supposed to go through to, 4:40, I think? But we mercifully get a break in the middle where coffee and stuff arrives. That's around 3. Apparently it's been left up to my discretion, so it'll be around, I've got it actually at 3:10. So hopefully all the good pastries won't be gone by then. And so we'll play that by ear. And then I've already told you about the GitHub repository. I think that's all the logistical housekeeping kind of stuff. Now, in terms of the course, so I wrote the paragraph that I used to apply for this tutorial here. It's a little bit outdated. I wrote this, it seems like years ago now. It's mostly still true. It's probably going to be better than that. But the motivation behind this is a couple of reasons. How many actual statisticians are in this room? Good, because you'd be very, very bored if you were already a statistician. How many of you are what you would call data scientists? However you define the word. Yeah. How many are developers? Okay, mostly developers. So part of the motivation for and this is kind of what I figured it would be, is to instill a little bit of statistical literacy, right? Because we all play with data. We're all worried about things like uncertainty and perhaps making predictions, perhaps estimating things. But we may have not had that background. Or if we did, it was in an undergraduate class, 3 years or maybe 30 years ago. And chances are that class wasn't very good. Mine wasn't. And so what this is designed to do is to give you some sort of pragmatic tools and also modern tools to use for kind of day-to-day data analysis. You got two things, you want to compare them. How do I do that? Well, you don't have to go back to your notes from undergraduate statistics. And then also doing it in a computational way rather than an analytical way, right? We're not deriving equations here. I might show you some equations for interest, but we don't need to know all of that. So that's the idea. And then also, some of you that already, how many do machine learning as part of their job or hobby or whatever already? So, and a lot of you have computer science backgrounds rather than statistical. And there's sort of a statistical and a computational side to machine learning, right? And so this is going to give kind of a statistical perspective rather than a computational one. Okay? So hopefully that will be beneficial to some of you as well. Okay, let's see, I've burned about 10 minutes there. How's the installation stuff? Here, let's do this. Blue stickies if you're ready to go. No stickies means it's in progress and everything's going well, or you just not follow, or not. You don't have to do all this stuff. They're better if you're hands-on, but if you just want to watch, you're welcome to do that. And yellow if you've got some issues that need to be attended to. Okay, all right. So I'll just go through here and try to get this going. You can turn this off for now. Yeah. If it all if it all hopelessly fails for you, you can always buddy up and pair program for this. Okay. Nothing worse than it's being a connectivity problem. Let that going out. Who's got another yellow sticky? this may be the solution to our problem here, at least for some of you. So MyBinder is a site that'll host repositories built on Conda and install everything for you, and then you can run it on somebody else's hardware without having to worry about all of this stuff. Who else is on here?
Back down to here, and then it's just been sitting there.
Our Conda packages, which are binary, the last one is PyMC3, and it's building and installing this for you. So that takes a while on my computer too. One more over here. Pandas, Seaborn. Save as. Okay, so some of you are having issues on the Windows front with Conda installing stuff. So I've added a file to the repository, or I'm trying to. Man, even git push is choking here. Hopefully this will work for those of you who are still struggling. All right, I'm going to let that run. And I think for now we should push on. If you're having trouble installing this, pair up with somebody. I think that's the best use of our time at this point. That's not going to help. That one's going to take a little time to run. It should have done it by now, but I think there are, because of the connection issues, it's probably pulling stuff down really slowly. I thought the Wi-Fi would be a little faster, but I guess that was bad assumption on my part. So for those of you who do have things up and running, to get things going, for those of you not as familiar with IPython notebooks or Jupyter notebooks, what you do is go into the directory where you've got all of the tutorial materials, and you type in Jupyter Notebook. And it should pop this up in your browser. And what we want to do is get into this notebooks piece here. And so my plan is to cover 4 things. We'll see how optimistic that is. It's fine if we don't get to everything. The first part was going to be a quick tutorial on pandas. How many of you already know how to use pandas relatively adeptly? Most of you do, okay. I may slide through that relatively quickly for the benefit of those who are not, but we won't perhaps spend as much time on that so we can get to the statistical stuff. The reason I did this is because data cleaning and preparation is probably 80% of the time that you spend on data analysis, irrespective probably of what domain you work in. And so it's really important, and pandas is a really important tool that feeds into all this other stuff. So this won't be a comprehensive, Wes McKinney tutorial, but it'll go through a little bit about how to import and manipulate data. And then the next piece will be an intro to statistical inference, primarily from a Bayesian perspective. And so, and that may be a little intimidating to some, but it's going to be super user-friendly, and again, not very math-heavy, very pragmatic. Teach how to do stuff like comparing two groups to one another for different types of data. And then get into an important topic called regression modeling, where you have 2 variables, and you want to compare how one variable predicts another. And then finally, if we have time, a little section on missing data, because missing data is a very important statistical topic that often gets overlooked by machine learners. So that's the plan. And again, if you're having issues, do pair up. Let me see how let's see how my binder is looking. Still running, okay. What this will do is allow you to run it on a remote server with all of the packages installed, but it looks like it's still cranking, so we'll move on. All right, so we'll open the data preparation one first. Let me blow up my screen. How's that look? Everybody read that okay? So pandas is a high-level tool for doing data manipulation and transformation that is primarily concerned with tabular data, so rows and columns. And it's extremely flexible. You can deal with a variety of different data input types and a variety of different variable types. And it's also extremely fast. The original designer of pandas, Wes McKinney, was extremely obsessed with performance, and as the result, pandas is a very efficient and capable tool for handling and transforming data. Its origins were in sort of financial data analysis, and so it's extremely adept at doing time series analysis. But really any arbitrary kind of matrix layout data with row and column labels can be accommodated. And it's got a ton of useful features, including sort of built-in handling of missing data, again, a topic I'm going to revisit later. One of the most important things that it does is that it allows data tables to be aligned, so it's got indexes on rows and columns, so that it's very smart about how tables are joined together in sort of a database type of an approach. And it's really good at doing things like slicing and indexing, reshaping and pivoting. You can go on, and of course there's books and tutorials written about this. Its two main features are a couple of data structures that it has. The first is called a series, and series is essentially just an array, essentially a NumPy array, but the added attribute that it has is an index, and by default it gives you an index of ordered integers, but you could give it other labels as well. So an array or a series has kind of two main attributes: the underlying values, which is just a NumPy array, and this index, which is its own object type. And so if we're not interested in having integers as labels, for example, we can give them labels. So let's say this is some biomedical data. This is bacterial counts from a microbiome study. And so we've got 4 count values, and now we're going to give it index labels corresponding to the genus of that bacteria. And you can use those labels then to pull out the value that you need. You can do fancier indexing by, let's say, pulling out only the ones whose names end in bacteria, and so it leaves out the others. You can check for membership. But you can still use, underlying all of this is still an integer index, and so you can go in and use positional indexing if you want to. And you can decorate your series with names, both for the data and the index itself. So these are particular, I said it was genus, these are phyla of bacteria, and I'm going to call this counts because that's what they are. One of the nice things is that it's really tightly integrated with NumPy. So NumPy functions not only work on pandas data structures, but they return a pandas data structure back, right? You would expect it perhaps to convert it to a NumPy array, but it doesn't do that. So you retain all of that high-level stuff. We can filter according to values. So let's say we only wanted the counts over 100 or 1,000. And one way of thinking of it is as sort of an ordered key value store. It's almost like a dictionary with an ordered dict, in the sense that it's got labels that you can index by, but they do have orders based on the underlying index. We can pass any sort of index that we want. So, for example, if we give this an index that includes a phylum, a name that doesn't exist in the original data set, what we get is perhaps a little surprising to those not familiar with pandas. It excluded the one that we didn't specify in the index, and then it added the one that's in the index but doesn't have any data. Okay, so the index is super important, right? The index determines essentially what is done with the series. And then lots of very useful built-in methods, so we can check, which ones are null. So in this case, we have this missing. So I told you missing values are automatically accounted for. You can see this here. So NaN, not a number, is our placeholder for missing values. If you come from the R world, R has had missing, the missing value is kind of built into the language because it was designed for statistical analysis. In Python, it's going to come from third-party packages like pandas and NumPy. And so this is the alignment that I was telling you about. So if we go back to that original bacteria series, and let's say we want to add that to this one, what happens? Well, we end up with an index with 5 elements rather than 4. We added two series of length 4, and we got one of length 5. And the reason is because, again, it respects the indices of both of these series. So it creates the union of the indices, and where data was missing from one or both, it's got not a number. And you might have you might be a little curious as to why they're both nan when we had data for one of them in this one here. And the reason is you add the nan propagates, right? You add missing to 5. The answer is missing, not 5. You can't assume missing is going to be 0. So generalizing the series is the data frame. So this takes, you can think of a series as being one column of data, if you like. Well, in practice, if we're using this for data analysis, we're usually dealing with more than just one column of data. We're dealing with multiple columns with multiple data types, and we need them all in one place because as each column represents a variable, each row typically represents an observation. So in this case here, each row represents not just a patient, but a patient observation. So this is actual microbiome data from work I did a few years ago, where essentially these were kids with necrotizing enterocolitis, and they had either stool samples taken or gut samples taken. And those samples were assayed using PCR for bacteria to see how they compared. And so each of these is the count of a particular phylum of bacteria in a particular patient. So each row represents some sort of independent, usually independent observation. Right? So that's where the data frame comes in super useful. By default, they're sorted by column. The columns are sorted by name, but you can realign them simply by indexing. So if we wanted phylum first, we just pass an index with that order, and it'll return the data frame ordered as we like. And an important thing to notice with pandas is that almost everything is not done in place. Right? So it will return you the new object, the new data frame, leaving the original as it was. And that seems a little inefficient sometimes, but it's really useful when you're doing iterative data analysis and data exploration, because you don't want to accidentally change something along the line during your analysis, because it's hard to go back to the original data. You'd have to go back and rerun, import the data, and remanipulate it. Here, you can always go back and use that original data frame in its original form. The important thing about the data frame is it's got this second index that corresponds to the columns. So we saw the index on the rows with the series. Now we've got the same thing for the columns, which presents a little bit of a conundrum when it comes down to indexing. Well, what is it going to index when you pass it a value? Well, if we want to access columns, we do that using a dictionary indexing. And when you do that, it returns you a series. So a single column gets extracted as a series. If you want to retain a data frame structure, you use this double bracket notation, which is just saying I want a data frame, but that data frame just has one column. What do we do about rows? If we're indexing rows as well as columns, we use the .loc attribute. And this is just an accessor for both columns, or rows and columns. So this will take the third, or the index 3 observation, which of course in Python is the fourth one. And it returns me a series, Notice that it's of data type object because it's taking a slice across variables which may be of different type, right? So it doesn't convert all of these, try to cast all of these to the same data type. It only retains the most general type. So in this case, it's an object. I'm going to skip the exercises for the Python section because so many of you already are familiar with it. But if you're new to pandas, do go ahead and try those. There are lots of ways of creating data frames because we get data in a lot of forms. You can pass it a NumPy array if you want to, but then you've got to add labels and indices, index labels if you need them. Here's an example using a list of dictionaries where each row in the each item in the list is a dictionary that represents one datum, because sometimes you get data iteratively over time, row by row rather than all at once. And that will create a nicely arranged data frame as well. A really important thing to remember about pandas data structures is that when you index a data frame or a series, you're always getting a view into that subset of the data set that you're looking at, rather than a copy. And this requires a little bit of caution when you're using them. So for example, let's say that we wanted to manipulate our data and say that actually index 5 here didn't have the count that we thought it did. There was actually a 0 there. Something went wrong. And so we're going to assign 0 to that. And you can see that you get a warning here because it is so easy to misuse this. And so, we extracted these values from the original data frame to get a series. So this is a series. But if we go back and look at the original data frame, that 0 is propagated over. And the reason is that you were always manipulating this data frame. You were just looking at a little piece of it. We're looking at a view of it. Best way to avoid that is, to make a copy. So now if we copy it and say, oh no, actually there were 1,000 in that one, and then we go back and look at bacterial data, it didn't change that to 1,000 because we actually made that physical copy, or that new copy, I should say. All right, I'm just going to put back the value that we accidentally changed. Makes it really easy to add rows or columns. So let's say all this data was from 2013. I could add a column called year, and all I have to do is pass it the scalar. I don't have to resize it, so it will broadcast it as necessary. However, you can't use attribute indexing to create a new column, and I've seen this happen over and over again with new users. Let's say I wanted because all of these columns exist as attributes as well as using indexing. If I go bacteria data, dot phylum, it returns me the view on that data. But it doesn't work both ways. If I want to add, let's say that these were all treatment patients, they were receiving a treatment of some kind, and then I look at the data, well, where's my treatment column? Well, at the end of the day, this data frame is still just a Python object, and Python objects have attributes. And so it didn't know whether to create a column or just to have an attribute, and it obviously defaults to an attribute. And so now we just have an attribute called treatment of 1, which doesn't really mean anything. It's not really data in that case. It's not data at all. Like, Python data frames, like Python objects in general, have other attributes. It's got, there's methods for joining and applying functions and so on. We just added another attribute with value 1, and who knows what it's for? They're very flexible. It's just not data. That's not how you add data to the data frame. So auto alignment. So when we add a column that isn't just a simple constant like we did with year, we've got to be a little bit careful. So what I've done here is created a series that represents this treatment, treatment control kind of thing. And notice I've only created one of length 6. So 4 zeros and 2 ones. If I add this as treatment, so here's how I'm supposed to do it, is to pass it using the dictionary notation, dictionary indexing notation, I get this. It actually worked, even though they're of different lengths, because indexing, right? Because indexing is great. And so it put nans here, which is a reasonable thing to do. It doesn't work with other data structure types, I should say. So if we have one called month that's just a list, and I try to do that, and it's only of length 4, it breaks. Because it doesn't know what to do with a NumPy array or a list because it doesn't have an index. So it threw up its hands, essentially. If it was the right length, it would have worked. So this, for example, works, right? Here's a list of the appropriate length with just Januaries in it. We can remove columns just by deleting them or using the drop attribute. That's not too surprising. We can always extract the underlying data. If at some point we don't need all of pandas' sugar, then we can strip it away and just look at the raw data anytime that we need to. That's not super interesting. One thing to note is that indexes are immutable. So if we don't like the fact that our first index is labeled, it has the number 0, it's supposed to be 15 for some reason, you can't simply replace it. What you've got to do is create a whole new index and assign that new index as the index attribute. The reason is that indexes can be shared among data frames. You can take the index of one data frame and assign it to another, and you don't want the carpet being pulled out from under you, or the rug pulled out from under you, having elements changed. If I were allowed to do that, it would change the value in both of these because they're referring to the same object, whereas if I simply swap out the index of one of these two, it wouldn't affect the other. All right, how are we doing on time here? 2:07. That's not too bad. One of the great advantages of using pandas, if nothing else, is that it makes the importation of data in whichever form that it comes to you in. I work with clinicians, and they like to give me spreadsheets. I've had data come to me in Word documents, PDFs, and things like that. It'd be nice if everybody stored their data in relational databases like they're supposed to, but the real world's not like that. NumPy is great too, but its data import mechanisms are quite a bit more limiting, particularly when you're dealing with heterogeneous tabular data. So the load.txt function, for example, which is what you would have used before pandas, requires you to specify a whole bunch of stuff, very cryptic signatures for variable types and so on, which was great at the time and then became a little tiresome, and then pandas came along and made everything nicer. So for example, let's look at this is some data we'll use later. These are Olympic medal counts scraped from the Olympic website. If I want to read that in to Python, I can use pandas read table function. And it's very flexible. You can specify the separator, whether or not to use one of the columns as the index, whether or not there's a header. In this case, there wasn't one. So I'm assigning names to it. And so in one function call, you can get a properly formatted and imported table. And this separator argument is great. It takes regular expressions. So occasionally you'll get for example, a table that has an arbitrary amount of spacing between variables, you know. And you wouldn't want to just say 3 columns or 3 spaces. You can use this, which specifies 1 or more spaces, 1 or more white space characters. We can scrape stuff from the web. This actually broke for me the other day because of another underlying library, HTML5 lib. I think it's working again now, although our internet appears not to be. So I'll abort that. Oh, now it's just hanging on me. Let's see. I think I'm going to punt on the rest of pandas. I've shown you most of the stuff that you'll need to do. Oh, there you go. It failed. Okay. It's failed nicely now. Just briefly, CSV values. CSV is just a special case of read tables where the separator is built in with as commas, pre-specified as commas. You can, if there are perhaps rows with bad data or things you want to exclude for some reason, you can skip the rows. You can, if you've got a very large data set and you want to process the data chunk by chunk, because your resources are limited, you can do that. So I can, let's say I just wanted the first 4 rows. Maybe there's 30 million rows of data, not uncommon for genetic data. You can just pull in a little portion of it. So this is just the first row. Or in fact, there's an argument called chunk size that you can specify that returns this weird object called a text file reader. And this text file reader is a Python generator. And what it will do is pass you things 1 chunk at a time. Oops. Okay, so chunk by chunk. So here's the first 15, here's the next 15, and so on. And so in this case, it just so happens there are 15 rows for every phylum. You can see the taxon changes every time. I could calculate taxon-specific, means or whatever here without having to import, potentially, again, millions of rows into memory. Remember, all this is being done in memory, so these are actually pretty useful things to know. Hierarchical indices. What the heck? Because they're so cool. So this is more of this microbiome data. This one is properly... So the thing about the data that we were looking at before, I mean, it's not a big deal, but... the thing about these Macs is that they got rid of the escape key when the caps lock key was sitting there, just waiting to be removed from my keyboard. If we look at the index of our bacteria data, you can actually see. Oops. Isn't there an is unique? Ah, there we go. There's an attribute that tells you whether or not it's got a unique index. I guess that one, I think I changed that one. But in any case, the data, remember, has 1 row not for every patient, but for every patient observation. And we sometimes want an index that represents that kind of unique combination. And so what we're really dealing, the actual data here is, these are, remember I said before that this data is a sample taken from the tissue, the stomach, and then the stool. And so every patient and bacterium has a count associated with it. And what we can do, rather than specifying a single column as an index, so if I used either of these 2 columns as an index, they wouldn't be unique because there are multiple patients and there are multiple taxa. But patient by taxa, it's going to have a unique index. And so when I import it, I can actually specify which, I showed you this before. Last time I said index call equals 0. Here I'm going to specify 2 columns rather than just 1, which seems a little odd. And so what happens is it creates what's called a multi-index, where now every row is indexed not by a single integer or label, but by a tuple of labels. So what it really does is it allows you to represent kind of multidimensional data while retaining the tabular format without having to go into 3 and 4D data structures. So now I can index stuff out, but I've got to do it. Oh, yeah, this is the old, yeah. API changes, hadn't changed this one. This should be LOC rather than IX now. They've deprecated IX. Used to be IX. So now I can index out the first, or looks like the third row here by passing it that tuple. But I can still pass it a single index for one of the components of the hierarchical or the multi-index. And so now I get the whole proteobacteria, and you see now that there's a single index rather than a multi-index because I've just taken that subset out. So that's really great. You can similarly do a cross-sectional method for indexing, but I don't usually find that as useful. And we can reorder them as well if we want one on the inside versus the other. Although the nice rendering on Jupyter, notice it takes repeating cells and unifies them so they're a little bit nicer to read. I'm not going to talk about relational databases, I think. And let's see, what time is it now? 2:16. Now we better push on. So this, I'll leave this one with you. This is a nice example. This is actual data that was compiled from the Ebola outbreak in West Africa and compiled by Caitlin Rivers on a GitHub repo. So if you're looking for really big, ugly, messy, but wonderful data, that's a good one. And this represents a really nice real-world example of what you have to do to clean data up to make it analyzable. And this example shows how you do that with pandas, because each table's got different labels associated with it. It's got data in different formats. It's got missing data and all sorts of other things. And this you know, so for example, here's one from Sierra Leone, and it's got, you know, date and variable and a bunch of provinces. And then this one here's got, you know, description rather than variable. And it's got inconsistent descriptions here. This uses underscores. And, you know, so if we wanted to, you know, extract all of the, let's say, new cases of Ebola, if we were doing surveillance on how the outbreak was progressing, we'd have to somehow clean this up. And this is a nice example of how you might do that. So perhaps you can do this one, you know, on your own or on the break. But I think I'm going to push on, given our earlier technical difficulties, and get into the statistical analysis. Okay, let's open notebook number 2. And then I'll try to get through this before the break. All right, so this is going to look at, it's kind of an easy introduction to how you statistically compare data from two groups. First, looking at outcomes that are continuous. So they got values that are, you know, measured, let's say on the real line, you know, measurements like height and weight and blood pressure, those sorts of things. And then we'll get to binary outcomes, which are also common. Dead or alive, male, female, true, false, those sorts of things. So just in general, you know, what we mean by statistical inference is we're trying to learn from data that is either incomplete or error contaminated. And by error, we don't necessarily mean mistakes. we just mean variability, right? If there was no variability or error, A, we wouldn't need statisticians, yay. And B, we'd only have to observe, and the reason we wouldn't need statisticians is that we'd only have to measure one of everything, right? You just need one thing, and then you'd know everything there is to know, right? If it didn't change. And the approach that we take, so if we're interested in whether or not two groups are different from one another, one bigger than the other, did my experiment work? Does the treatment improve, the probability of surviving cancer, or does it make your IQ higher if you take this fancy new drug? The way we would do that is using a statistical hypothesis testing framework. And this is what how many have had undergraduate statistics? Everybody, right? This is what you learned, right? You learn t-tests, chi-squared tests, non-parametric tests, ANOVAs, all this stuff. That's all statistical hypothesis testing in action. And the goal of statistical hypothesis testing is actually not to evaluate the hypothesis that you're interested in, it's to evaluate a null hypothesis. That's usually, sometimes, a lot of the time, not related really to what you're interested in. So if it's, let's say, does my drug increase survival of cancer patients? Well, the null hypothesis is no, it doesn't. That it has zero. That's usually what it is. No, zero effect. Survival is the same with or without this drug. And so what we do, we carry out a test that has one of two outcomes. We either reject the null hypothesis, or we do not reject the null hypothesis. Doesn't say anything about your research hypothesis, just the null hypothesis. And the rejection occurs when some test statistic that we have, t statistic, z statistic, etc., chi-squared statistic, is higher than some pre-specified threshold value, right? So you probably remembered looking at tables like this, right? You looked it up in a textbook. And if it was, and then you got to choose the level at which you thought it was significant. Okay? And notice it doesn't say anything about what you're interested in, which is your research hypothesis. And so what we say is that we reject the null hypothesis. And that's pretty much all that you can say. And depending on how you choose your null hypothesis, it may not even be meaningful, right? Zero may not be the proper comparison for what you're trying to do. No drug has zero effect. I mean, feed somebody sugar pills and you get non-zero effects on things. So it can be very hard to interpret the outcomes from statistical tests, and there are a lot of subjective choices that go into setting this up. A, which statistical test to use, which null hypothesis to test that I just showed you, which significance level, right? What's the default statistical hypothesis testing level? What's the magic number? 0.05. And it's arbitrary. It is arbitrary. It was traced back to Ronald Fisher, and it had a paragraph that said something about 1 in 20 was a reasonable level to choose. So Ronald said so, and that's why we do it. Sometimes you get 0.01 in medical stuff. But it's entirely arbitrary. 0.04, you can't publish your paper, or you can publish your paper. 0.06, you can't. Those sorts of problems. So choices are often based on these arbitrary criteria, statistical tradition, and the evidence is very indirect. Again, it's testing not your hypothesis, but something that may or may not be related to it, and it generally overstates the evidence against the null hypothesis. So, instead of testing, a better approach, a more informative approach, is to use a estimation-based approach. And this has nothing to do with whether it's Bayesian or frequentist. But rather than testing whether or not two groups are different, yes or no, rather estimate how different they are. It might be 0, it might not be 0, and also give some measure of uncertainty around that estimate. And that's what we're going to use here. So how many of you have taken Bayesian statistics, either informally or formally before? Not as many. So you usually don't get it in undergrad. Again, my education is a little bit outdated. I was an undergraduate in in the 90s, but I certainly didn't have it in any of my courses. And you might have gotten it a little bit when you talked about probability, because Bayes' formula can be derived from conditional probability, and that might have been the only thing. Oh, here's Bayes' formula as a result of conditional probability, and that's it. Most people didn't really use it. I'm going to give you the quick rundown about what it is and why it's useful. Andrew Gelman, who's a big Bayesian, says this, what are Bayesian methods? They're practical methods for making inferences from data using probability models, that's the key point, for quantities we observe and about which we wish to learn. And the key thing was probability models. This is probability modeling writ large. So everything the nice thing about Bayes is that everything you do, doesn't matter what model you're fitting, what kind of data you're analyzing, all of the inferences are in terms of probability statements. So this is going to be my notation throughout here. We're going to talk about things we don't know. These can be parameters in a regression model. These could be unknown means of a treatment or a control as theta, or some Greek letter. And then our observations are data or y. And so what this is saying, this expression says the probability of theta given y. So the bar is a conditioning. We're conditioning on y. What it's saying is, what's the probability of my hypothesis being true, of my effect size being greater than 6, something like that, given the data that I've observed. So right away, that should strike you as a little bit easier to interpret, right? This is a direct statement about what we're interested in, right? What's the probability that these two things are, the difference between these two things are different from 0, given what I've observed in my experiment? I've gone out and observed stuff. What does the evidence from that say about what I don't know? Okay. So, couple benefits. Ease of interpretation. Because they're probabilities, so we're going to be dealing with probability distributions, right? Normal distributions, binomial distributions, and so on. It is a nice summarization of uncertainty. They've all got estimates of variance associated with them. You can incorporate uncertainty into parent parameters. We sometimes know stuff about these parameters before we go and fit our model. We can incorporate those in. And it's actually very easy to calculate summary statistics and things that we are interested in after we've gone in and fit our models. So the big difference between Bayesian and frequentist and or classical statistics is this. Essentially, if you're a frequentist, that's Ronald Fisher right there. Looks like Santa Claus, but it's Ronald Fisher. And the way frequentists look at the world is they view data as being random, right? They're random. They're the outcomes of random processes, flipping coins, doing scientific experiments, doing A/B testing for websites, that sort of thing. And so we consider those to be random. And then model parameters, or things we don't know, are considered fixed, right? The effect of the quality of your website, the effectiveness of this new drug. And so we're going to condition on those. And so what they say is, so their notation is slightly backward from what we did before, right? We had theta given y, here we have y given theta. So we're going to condition on these unknown things and say, what's the chance of us seeing what we saw if this thing was true? So you see, it's a little more indirect, right? We're going to assume what we don't know is true and then see how likely what we observed is. It's not wrong. I'm not saying it's wrong. There's nothing wrong with hundreds of years of statistics. It's just more indirect. And so what statisticians do, who are frequentists, they derive estimators for things, right? Things to estimate the variance, things to estimate the mean. And they choose them based on various criteria, right? So-called optimality criteria. Like, we might want them to be unbiased. We might want them to be have the minimal variance, as little variability as possible. Most efficient in terms of use of data. And one example is the estimator for binomial probabilities, right? Coin flips and so on. An estimate of, let's say, the probability of heads in a coin, all statisticians have to use a coin example at some point, here's mine, is the number of, let's say, heads over the number of times you flip the coin, right? So if it's around 5 over 10, for example, 50%, that's an unbiased coin. That estimate 0.5, or whatever that ratio is your frequentist estimator for the probability of heads. And we choose it because it's known to be unbiased and minimum variance. Okay? Bayesians, as I suggested, it's the other way around. Bayesians view their data as fixed. It used to be random before we observed it, but once you record it, right, once you write it in your lab notebook, it doesn't change. When you go back the next day, they're not different values. So they once were random, they're not anymore. So we're going to condition on those. We're going to hold those as fixed. Then our parameters, our model parameters, are considered to be random, and I'm going to put random in scare quotes. We don't necessarily mean that they, change. Survival rate of, under drug A doesn't mean that it changes all the time, although it might. What we're saying is we're going to use probability to define our uncertainty in that parameter. And the more we know, the narrower it's going to get. Right? So we're using here probability as a state of knowledge rather than as some stochastic sort of thing, definition of randomness. If you're a Bayesian, you don't need to develop any estimators, which is great because I'm terrible at that. So the only variable or the only estimator you need as a Bayesian is Bayes' formula. This is obviously what this paradigm of statistics is named after. This can be easily derived from the definition of conditional probability, as I suggested before. And it looks like this. Let me give you a quick tour of Bayes' formula. I already showed you this, right? This is what Bayes is all about. What's the probability of these unknown things given what I've observed? This is known as a posterior probability. The reason it's called a posterior probability is that it's what you know about theta after observing y. So posterior means not your butt, it means before. Prior probability is what we know about theta before we did our experiment or observed our data or whatever. And in between that, we have this thing called a likelihood, a statistical likelihood that does describe the variability of the data. Frequentists are all on board about this. This is common to all varieties of statistics. These classical statisticians don't recognize. So we take this initial probability, our initial state of knowledge, we update it with information from our data, and we get a thing called a posterior probability. This thing down here is essentially just a normalizing constant. Probability of y, the probability of our data. It's kind of a weird thing. Ostensibly, all it does is it normalizes, because remember, all the PR means probability. So these, remember the rules of probability, right? They have to sum to 1 or integrate to 1. They have to be between 0 and 1, all those sorts of things. This ensures that that's a probability and something that's not something that's unnormalized. Okay? It turns out, though, this normalizing constant is a huge pain in the butt. And the reason it is because what it is essentially the numerator integrated over all of theta. You just take those thetas and integrate them out. It looks like this. Well, if you're trying to calculate those posterior distributions that we're really interested in, this becomes impossible, right? So I can do univariate integration. I still remember how to do that. I probably need textbooks to help me with two-variable integration. Anything higher than that, forget about it. And even if you're an expert mathematician, hundreds or thousands, you can't do it analytically. So for most problems of interest, directly calculating posterior distributions is impossible. And that's one of the reasons that Bayesian approaches have been kind of on the sidelines relative to classical statistics. They were just hard to calculate. But now we have computers that allow us to implement algorithms that we're going to see today. Okay? Priors were sort of controversial with respect to Bayesian statistics. Remember, priors is, characterized as what is known about the unknown quantity before you go out and observe things. Well, they're viewed by some as being subjective, right? Depends on who you are, right? What you know about something. And so you know, the old, you know, trope was that, well, you could just make your analysis say anything you want by fixing the priors to make it that way. And that's absolutely true, but you got to write your prior down. You got to tell us what it is. And if your model is sensitive to your prior choice, you know, you got a problem. Secondarily, all of statistics is subjective. I already showed you things about the p-values, right? Choosing alpha equals 0.05, you chose to do that. It may have been statistical tradition, but it was chosen and somewhat arbitrarily chosen, which test statistic to use, which data to collect in the first place. There's no such thing as objective statistics. End of story. So all you got to do here, you know, again, you have to be honest about what your information state is beforehand. You can make priors that are uninformative if you really want the data to speak for themselves. But typically in science, we want to build upon previous work, right? You want to take what's known and improve upon it. And it allows us to do this. Likelihood functions, I won't say too much about that other than, again, it's the evidence in your data. It contains all the information that's used to update this information state. And there's a nice property called the likelihood principle that says that the likelihood function contains all the experimental information about from your data that's relevant to your model, and that's just really nice. How do we do Bayes? 3 easy steps. First step, specify a probability model. Right? So we got to specify, we got to completely specify our model. So priors for the unknown parameters, what your data likelihood is, what your data is in general, any covariates, any missing data, just write it all down and then code it up. And we'll do that in a little while. And this is the tricky part for some, right? What prior should I use for different things? And this is what I'm going to show you a little bit later down, further along. And so the body of knowledge that's most important for being a Bayesian is probability. Being familiar with probability distributions and how probability works. And this kind of just takes a little time to get a little intuition. You know, this is count data, so I'm going to use a Poisson. This is data for binary. This is a prior for a variance parameter. Well, it has to be positive, so I'm going to choose a gamma. And these sorts of things. And there are always references for everything, but there's always a lot of examples. There's again some statistical tradition involved here too. But it just takes a little bit of familiarity. Just a quick overview. In general, we have a couple different kinds of random variables, discrete and continuous. So discrete ones are defined at particular points. So, trues and falses are, discrete values. There's no halfway between true and false. Counts of things, right? We can only count in integers. There's no decimal numbers. So here's and so they have these probabilities that look like this. This is a Poisson distribution, often used to define counts of things. That's its functional form. So the data can look like 0, 1, 2 because they're counts and so on. It's got one parameter, lambda, that has to be greater than 0. And its expectation is the same as its variance. So there's kind of a suite of discrete parameters that you can use here. And so I'm going to pull out, oops. I forgot to run all of the prior cells here. Uh-oh. You know what it is. I did the mortal error here. Source, activate. What is it called? Stat PyCon? I didn't activate it. All right, so I'm just going to draw. So I'm going to specify a Poisson distribution, and I'm going to give it a mean of 1, and I'm going to draw 1,000 samples or 10,000 samples. So I can calculate its mean, and that's what its distribution looked like. Throughout this tutorial, I'm going to use a package for Bayesian statistics called PyMC3 that I'm a developer for. However, this tutorial is not going to be focused on that software in terms of its details and technical capabilities and so on. We're going to consider this kind of a black box, right? We can do statistical analysis with a whole bunch of different types of packages, and so I don't want to focus on PyMC, but we will use it kind of to generate things like this. Just as a side note. Continuous random variables, on the other hand, are defined over an interval, right? So let's say between 0 and 1 if we're talking about a probability, or from positive to negative infinity, the whole real line potentially. The most famous one being the normal distribution, right? It's the most important distribution in statistics. It's got a mean and a variance. The mean can be any number on the real line. The variance has to be positive because you can't have negative variability. And its functional form looks like that. And similarly, again, you don't have to know necessarily all the mechanics, but just how to parameterize it. So here's a normal distribution with a mean of -2 and a standard deviation of 4. And so sure enough, the mean is around -2. The standard deviation's around 4. And it looks nice and bell-shaped, sort of, if I had more bins on my histogram. About every 2 months, you'll see an angry tweet from me about histograms in Python. Okay, step 2, calculate a posterior distribution. So we've specified a model. We'll show you how to do this step by step in a minute. Calculate that posterior distribution. But remember, this could be the hard bit, right? So the first one is the conceptually hard part, how to specify your model. That's usually what people have trouble with, is just writing your model down. The hard part technically is getting this posterior distribution. Can't do it analytically, so we do all sorts of approximations. So all the software, all the use of PyMC today, all it's going to be doing is approximating a posterior for us. And sometimes those approximations can be really good. Sometimes they can be lousy. So step 3 is always check your model. Check it. I mean, this should be the case no matter what kind of statistics you're doing, but it's particularly important for Bayes because this is model-based inference, and so the assumptions that you use in your model are usually, by and large, unverifiable. And so you got to go in and see, does the model actually fit the data? Like even the data, I'm not even talking about like out of sample stuff. The data that was used to fit the model, does it look like something that could have come from that? Do the conclusions make sense? Are they reasonable? Are the outputs sensitive to changes in model structure? So this whole prior controversy I was talking about. Go in and see if choosing somebody else's prior or a slightly different prior completely changes your inference. If it does, you've got some explaining to do, or you may have to go back to the drawing board. If it doesn't, you can be sort of happy. So model checking. All right, let's get into it. So we're going to do the simplest possible statistical analysis. I said comparing 2 groups. We're going to start by just looking at 1 group. All right? So we're going to do statistical inference for 1 group. And we're going to use a data set here. This is a popular data set. It's a radon data set. Let me get rid of my toolbars and stuff so you can see the pretty pictures that I stole from the internet. So radon is radon gas is a radioactive gas that causes cancer. It's the biggest cause of lung cancer amongst non-smokers. And it usually just seeps into your house from the ground, right? So this picture kind of shows from the groundwater, gets into, if you got a basement, you're sometimes more susceptible to this stuff. It comes in through your shower and stuff. On my house in Nashville, we had high radon readings, and so we had to, get people to remediate and put a big plastic thing around it, and this little pump that blows it out into my neighbor's yard. And so, so that you don't, so it's a chronic thing. So if you're in somebody's house for 2 or 3 days with radon, you shouldn't be worried. But if you live there every day for your entire life, you could end up with lung cancer, which is bad. So, so this is a data set from the EPA, radon readings in households in Minnesota. we're going to focus, just to keep it simple, on a single county in Minnesota, Hennepin County. Anybody here from Hennepin County, Minnesota? I don't even know where it is. Is it Minneapolis? Okay. Yeah, I picked one of the bigger ones, so that makes sense. And so let's say, so the EPA says that if the reading in your house is over 4, that's picocuries per liter, you should seek remediation. Another arbitrary threshold, right? If mine's 3.9, I'm probably going to remediate, but I'm going to pick an arbitrary threshold like that. So let's say we're interested in whether the mean log radon value is greater than this threshold value. And what's the probability, this may be even more important, what's the probability that any randomly chosen household has one that's that high? They're two slightly different questions, right? So, pulling out my Hennepin data, so here's my pandas in action. Query is a really nice method in pandas. You can write little, so that you don't have to do all this dot notation. You can just write a little string query and it will pull it out. And I'm going to pull out the log radon value. And this is what it looks like. Notice, oops, symmetric, kind of bellish shaped. Thinking of some distributions here. And we've got 105 observations. Okay? All right, step 1 of Bayes, right? Write down your full probability model. Okay. Typically, this requires 2, maybe 3 things. Your likelihood function, your prior, for sure, right? So let's start with the likelihood function. So bell-shaped, weirdly bell-shaped. So normal distribution. We start with something easy. We're going to start with the normal distribution. Okay? Looks kind of normal-ish. Who knows? Let's start with that. Again, we're going to check the model later. So if you're wrong, no big deal. So here's what we're saying. Y, which is the log radon, distributed normal with a mean and standard deviation. So that implies there's 2 unknowns here, right? Mu and sigma. So we need 2 priors. How do we choose distributions to use as priors is the big question. There's a couple of considerations. A, discrete versus continuous, right? If you have things that are, fractions of integers, you shouldn't be using discrete parameters because you'll never get there, or discrete distributions because you'll never get there. The support of the variable, what I mean by that is where it's what values over which it's defined. So some distributions are only defined by positive numbers, for example, or only on the 0-1 interval. And so you got to choose that appropriately. And then your available prior information, which may be relevant. You might have information, a whole bunch of previous studies about some of this stuff. Well, you could pull all those in and plot them and say, oh, looks like it's gamma distributed. I'm going to use that, okay? So for the mean can be positive or negative. This is the radon on the log scale, so it can be negative. Otherwise, if it wasn't on the log scale, I wouldn't be doing this. So I'm going to arbitrarily center it at 0 and set a variance of 100, so a standard deviation of 10. So it's a normal distribution, yeah, but the variation is so wide that it's almost flat. So we're choosing what we sometimes call a non-informative prior. There probably is lots of prior information about this, but I don't know what it is. And we're just going to let the data pick appropriate values. Standard deviation, well, we know that it has to be positive, right? Can't be negative standard deviation. And, it's not going to be in the thousands or millions. These are log radon measurements. So I'm just going to pick a uniform value between 0 and 10. I know that it just can't even be even close to 10. So I'm going to say uniform, it can be anything between 0 and 10. Again, if we're wrong about these things, we can go back and check them. All right, now let's write this all down. So here's how we specify it. So one of the reasons I'm using PyMC3, aside from the fact that I develop it, is that it's really easy to write this stuff down without doing a lot of programming. So here's what we do. We create a model. We're going to call it radon model, and we do that with a with statement. This is a context manager, for those of you familiar with that term. And then inside this model, we can define our parameters. And so I'm going to set my mean. See, it almost looks like you write it down on a whiteboard, right? Except you have to give it a name. And then sigma is uniform between 0 and 10, okay? So, done that part. And again, lots of software choices. Stan, JAGS, there's one called MC. Even commercial software is getting into the action now because they know it's good stuff. But we'll use PyMC here. All right. And the likelihood then is normal. We said that, right? But see here, notice the mean and standard deviation aren't integer values because they're unknown. They're the priors I just defined. So this is essentially y. I called it dist here. I should have just called it y, right? Y, just to be consistent. And then if you have data associated with a particular variable, you pass it as an observed argument here. So we're saying, here's my data. So this defines it as a likelihood. Okay? So I hope pretty relatively easy model specification. All right. Now, here's where we calculate our posterior distribution. I'm going to completely black box all this stuff, right? There's a whole other tutorial that I can give about MCMC and variational inference and approximations, and it's all super interesting, but that's not what we're here for, right? We're here to teach you a little bit how to do this stuff, methods. And so we're going to black box this stuff and you just have to trust me that it's generating good posterior distributions. Out of interest, we are using a numerical approach called variational inference that approximates the unknown true posterior with a known distribution that it kind of optimizes until it gets it as close as possible to the true. Okay, and so it'll go in and it's actually done relatively quickly. So it's nice and generic here. It just says fit the model. Do what you got to do. And then I'm going to pull 1,000 samples from it to get an approximate posterior distribution. And so now I can plot some of this stuff. So let's look at the mu. And this is on the log value. So I'm actually also plotting a reference value of log 4, because remember it was 4 picocuries per liter. And this shows some pretty interesting stuff. This is the posterior distribution of mu, which is the mean expected value of log radon. Here's the critical value. Again, admittedly arbitrary, but sometimes our arbitrary values are policy related and we can't do anything about them, right? This is one of these cases. And this is where the ease of interpretation kicks in. Once we have this posterior distribution, we get a lot of stuff for free. We get this whole distribution of values. So from Bayes, you don't just get a point estimate. You don't just get a mean. You get an entire distribution of values. And from that distribution, we can extract the mean. We can extract what we call a credible interval, a probability interval that defines our uncertainty in it. And you get all of that for free once you've calculated it. And so what this is saying is that the true value, there's a 95% chance the true value is somewhere between 1.2 and 1.5 on the log scale. And this is interpretable as a direct probability statement. So you may have in the past calculated something called a confidence interval that cannot be interpreted that way. Okay? Confidence intervals are statements about the repeatability of the experiment. It doesn't really say much about the precision of the parameter. This you can actually write down. There's a 95% probability the true value is between this point and that point, given my data. Full stop. And then, here's the cool thing here. What this is saying up here is that about 84% of the values are less than this critical threshold, 4 picocuries, which on the log scale is 1.4, and 16% chance that it's greater. So we've already answered that first question, right? And our first question was whether the mean log radon value is greater than 4. Well, there is a 16% chance that the mean value is greater than 4. So we have a nice, again, measure of uncertainty around an estimate. The next thing we want to do is, well, what's the probability that a randomly chosen, arbitrarily chosen household in Hepburn County is greater than 4? Now we got to do prediction. We just did estimation. We've got an estimate of something. Now we want to predict, right? This is a prediction, right? We're saying, put on your Karnak hat and predict. And so we're going to do something slightly different. because prediction is partly a function of what we know about the parameters, but it's also a function of a stochastic process, right? A random process. Some houses are, some houses aren't, irrespective of how much we know about the parameters. And so we have to use something called a posterior predictive distribution, which is another integral. But that's okay, we get this one. This is another thing we get for free after we've done our sampling. We're going to call Z our new unknown thing. And so what we're interested in, what's the probability of Z, in our case, some house greater than 4, given Y, what we've observed already about a bunch of other houses. And that's an integral of, here's our, recognize this, right? This is our posterior. And then this is the random process. This is generate me a new house. Let's see what its radon is. And then you integrate over theta. So we're integrating over theta means we're accounting for the uncertainty in the things we don't know about. So it all fits really sort of philosophically satisfying way of dealing with things. Okay? And we can estimate this just from the posterior samples that we took. We don't even have to go back and do any sampling. So we're going to take our mu's and our sigmas. Mu's. So these are the samples that I drew from the posterior distribution. Same thing for sigmas. And I'm going to draw from the sampling distribution, which is normal. We saw Hennepin County's log radon is kind of normal. There it is. So now I've got a whole bunch of radon samples. Let's see which ones are greater than log 4 and take the mean of it. 48%. Wrong value. So there's a 48% chance that an arbitrarily chosen house in Hennepin County has dangerously high radon levels. Actual usable, actionable information, very direct information. So this is kind of an example of why we like this stuff. Any questions about that so far? Yeah. So it's just an estimate. That distribution was just an estimate of the unknown parameter. So if we measured all the houses in Hennepin County, there would be no variance. We would know exactly what it was. So there'd be no uncertainty about it. But there's still a stochastic, there's still a normal sampling process going on for individual houses. So yeah, it may seem a little weird that it was only 60% chance that it was higher, but 47% of the houses are greater. Well, it's because that's just the mean. Yeah, there's also a variance associated with it. Yeah.
So line 18, is that why I might get a slightly different answer than you did?
Yeah, I've drawn, yeah. If we drew more and more samples, well, there's two sources of uncertainty. One is I did a random fitting here, although if you use the same random seed, these should be the same. So yeah, if we use the same random seed here, we should have gotten exactly the same answer. Yeah. Remember, these are approximate posterior distributions. So I've done sampling to estimate my parameters, and then I've also done sampling to estimate the posterior predictive. So they should be in the ballpark, but they won't be to 5 decimal places for sure. How are we time-wise? Ooh, getting close. Okay. All right. This is great, actually. I'll get pretty close to finishing this by the break. So here's the step 3 that people always forget or ignore, get excited. See, it's really easy because the software has gotten so easy to use. It's super easy to get an answer that looks great that is totally meaningless. So it's always important to go back and check. All right, so how do we know this model is any good? Well, it's important, to look at this and see if it's reasonable. If you're an environmental scientist, does any of this make any sense? So see if it passes the sniff test. But more technically, you want to compare the model to the data that was used to fit it. And the technical term for this is posterior predictive checks. So what we're going to do is we're going to generate simulated data sets from our model, and compare the simulated data to the actual data. And the actual data should look like some sort of random draw from those simulated data, right? So if we simulate a bunch of data and it's over here and our observed data point is over here, we're trying to make the claim that the observed data could have come from our model. Well, it's not very convincing if it's not even in the same neighborhood, right? So we can choose a whole bunch of statistics to compare. I'm going to just compare them graphically here. So here's the green are the observed data, and the blue are the purple are the simulated data. And they, there are bumps and things that are slightly different, but they're reasonably close to one another. Right? I'll give you a better example of this when we do regression in the second half of the course. Yeah.
How would this compare to, let's say, doing k-fold validation sort of thing where you're putting some part of the data as test data, generating
Cross-validation? Yeah, you can do that. We sort of discourage well, you don't really need cross-validation in Bayes. Another issue with that is that it's not efficient analytically because you're throwing data. You're not using some of your data you want to use all the data available to you to estimate your parameters. You don't want to hold aside any of it to cross-validate. There are model comparison methods that I'm going to show you later, AIC, that can be shown to be asymptotically equivalent to doing leave one out cross-validation. So there are other metrics that will give you similar outcomes. All we're trying to do here is check just goodness of fit. We're not necessarily trying to optimize a parameter. We're just saying, here's my model. This is the best model I could do. And it looks like it represents the data well. Doesn't mean, ideally, you would have, now the best way to validate this is to go collect more data from Hepburn County and compare that and see if it still fits, right? But you always want to use all the data that you have in hand to estimate your parameters because data are valuable, even in the age of big data, and so you want to use all of it as efficiently as possible. This is sort of, there's another component of model checking that I won't get into, and that has to do with model convergence. So I ran a variational inference algorithm. There's another algorithm that you've probably heard of called MCMC. And there are sort of mechanistic checks that you have to do to make sure that all of these algorithms have theoretical guarantees that they will work if you run them long enough. But that doesn't always turn out in practice, and you sometimes have to do convergence checking. But that's, again, more of a technical thing. It doesn't really have to do with kind of the philosophy of building Bayesian models. And so we'll set that aside for the time being. Some sort of model checking is important, though. Here's another type of model checking, prior sensitivity. So remember, I picked those priors just by going, that looks good, right? We don't know. I've used my intuition as a statistician. They may not be any good. So it's always good to either, go in and change the hyperparameters by an order of magnitude or something like that. Here, I'm going to go even further and specify completely different priors. I'm going to pass it what's called a flat prior. This is truly uninformative. It's a flat line from positive to negative infinity, which actually means it's improper, right? You can't have, that doesn't work. But we're going to do it anyway. They don't even have to be normalized. So a flat prior for the mean, and then a half Cauchy distribution for the standard deviation. And half Cauchy is kind of like a normal distribution with fat tails and only the positive half of it. So I'm going to put those in there. Everything else is the same. So I'm going to call this one prior sensitivity. So there's that posterior. Here's the original. Here's the original posterior. And it looks pretty good. In fact, the mean is identical, and the predictive interval is slightly off. So not hugely sensitive to prior choice, at least based on the quick comparison that I did. So that should give you some degree of comfort that you haven't done anything completely weird. And the nice thing about this is, you can bring somebody else in that's, a radon skeptic or whatever, and they can put their priors in and see if the data should convince them with, maybe more pessimistic priors or something like that. It's very handy. All right, that was just what we haven't got to two groups yet. Here's two groups. Two groups with continuous outcomes. This is often the case, right? We want to compare two things. So this is actually made up data from John Krushke's book, which is really great. This is for evaluate the efficacy of a quote-unquote smart drug that's supposed to increase intelligence. And so these are fake IQ measurements from drug and sugar pill, right? And so, is the drug group bigger than the placebo group? Who knows? So let's do this. Let's tackle this problem. Now we don't have this fixed arbitrary point that we're comparing to. We've actually got another data set. So this is perhaps more common. So what we're going to do for the likelihood, and just for some nice variety, we're going to use a slightly different likelihood here. The thing about normal distributions is they have really skinny tails. So that, in other words, they're very sensitive to extreme values. They don't tolerate them very well. So after 95% of the values have to be within 3 standard deviations of the mean. The t-distribution is a slight variant of the normal that has fatter tails. So it's tolerant to, it expects outliers every now and then. Because you can see here we got this, really low IQ value here, maybe a couple really high ones here. So yeah, most of it's in here, but occasionally we get stuff and we don't want it to bias the mean, right? So I'm going to use a t. That's what the student t looks like. It's much uglier. But again, we don't care. We're just going to use PyMC's implementations. And there's an extra parameter. So t's got, in this case, a mean and a variance, or a mean and a standard deviation. But it's got another parameter called nu here, which essentially it's like a degrees of freedom parameter. And it defines essentially how close to normal it is. So if nu is close to 0, or sorry, if nu is very large, the t-distribution looks very normal, so the tails shrink. And if it's very small, close to 0, it has thicker tails. Okay? So it's got 3 parameters each rather than 2. So our likelihood function looks like this. We've got 2 of them, one for the drug and one for placebo. And each of these, we're going to say that the nu's are the same. That's a model assumption that I'm going to make that we could test if we want to. I'm also going to say that the standard deviations are the same. They look similar. The only thing we're really comparing here are the means. But again, we could generalize this model if we wanted to. Okay. Just to give you a little bit of hands-on time, and we will, after that, we will have a little break. If you have gotten this working by now, maybe Anaconda is still downloading, who knows? Go into PyMC3 and draw 10,000 samples from a student t-distribution, and it's just called student t in PyMC lingo, with parameter nu equals 3, and compare those to a similar number of draws from a normal distribution with parameters mu equals 0 and, standard deviation equals 0. That wouldn't work very well, would it? Standard deviation equals 1. So let's use this as a simultaneous work on this example, which shouldn't take very long, and go get some coffee, because I know I need some. And we will reconvene in 10 minutes. And I'll answer questions.
The fit function in the PyMC3 isn't bound.
Sure can. Most of you are back, so let's reconvene. So yeah, this was just to give a little bit more familiarity with the interface. So student t distribution, new equals 3, 0 and 1 for the other parameters are the defaults. For those of you not as familiar with Jupyter, if you do Shift Tab Tab, well, I guess you didn't. There's too many other things involved here. Hold on. Oops. If you do Shift Tab Tab on student T, it tells you the things that it expects. Although I don't have the defaults written down, do we? Oh well. First, you parameterize it with whichever parameters you want, and then call the random method, size equals 10,000, similarly with the normal. And if that works, you'll be able to plot something like this, which shows exactly what I was trying to describe before with my hands, is the fatter tails. So the blue is the student t, and you can see fatter tails down here. And conversely, normal's more peaked in the middle. So that comes in handy. Some practical Bayesian stuff there. All right, so that's the likelihood. So let's turn our attention to priors. So we need new, 2 mu's, and sigma. Oh, it looks like I did use two different sigmas. Okay, never mind. So same as before, normals. This time I'm going to center them around 100, just because it's IQ. I know something about IQs. Standard deviation of 10. Sigmas, uniform between 0 and 20. And then for new, I'm picking a weird-looking thing, and it's an exponential with a parameter 1 over 29. And this was sort of hand-tuned to describe the range of t's between being very heavy-tailed and very normal-like. That's all. That's kind of the degree of variability we're trying to describe. So this is what it looks like. So values sort of between 0 and 100 have enough prior probability that a lot of data will run them over. So the thing about priors is that you got to be careful of is never to assign 0 probability to values that could possibly be the true value, because you're multiplying your prior by your likelihood, right? And when you multiply anything by 0, it's going to stay 0. It doesn't matter how much data is trying to influence you. But even kind of thin tails, there's still probability down here, and if you've got data to overwhelm it, it will overwhelm the prior. So, so this is reasonably good. Okay. And so here's the likelihood. So the drug likelihood and the placebo likelihood, student T. There's nu, there's mu1, lambda 1. They're called lambda in student T rather than sigma. And then the observations are the drug IQ and the placebo IQ that comes straight from pandas, okay? Then, so the model's fully specified. We could just run the model now. But there are some particular, because we're testing particular hypotheses, there are other quantities that we are interested in that are simple transformations of the unknown parameters in our model. And so what PyMC allows you to do, and again, any other useful probabilistic programming language allows you to do, is to define what are known as deterministic quantities. And that's what I'm going to do here. I'm interested in 2 things: a difference of means, IQ versus placebo, and then a standardized effect size, where we're essentially taking that difference and dividing it by the square root, essentially the pooled variance, or the pooled standard deviation. So I'm defining these 2 things here. I could just say mu1 minus mu0. Wrapping it in this deterministic object lets the fitting mechanism save its values to a trace so that we're going to use them. Otherwise, it would kind of throw them away. So I'm going to call this one diff of means and this one effect size. And again, these are just deterministic nodes mean that they're completely determined by the values of their parents. That's kind of the technical definition. So you'll still get a distribution of them, but that distribution will be purely a function of, in this case, mu1 and mu0. Right? So at every iteration, it will subtract mu1 from mu0, and you'll have a whole distribution of differences here. This doesn't add any stochasticity to the model at all. Okay, so we're going to add that, and we're ready. Fit the model. Done. And let's look at, these are the parameter values. This is a little less interesting maybe here. Let's go straight to the, here we go. All right, so difference of means. So the mean difference is basically 1. So you get an extra, your expected increase in IQ is 1 point from taking this awesome drug. Only a 1% probability that it's 0 or less. And standardized effect size, yeah. Sometimes people are interested in standardized stuff, but this is kind of the one of interest. Okay, so our conclusion is that treatment group is greater than the control group. The probability that it's greater is 0.9. Sorry. Yeah, that's right. Sorry, it's confusing here. It's both a 0.99 probability of being 0.99 greater, just by chance. So a point greater with 99% probability. Okay. Let's do an exercise. So there's a data set that I use in my class from time to time. It's Nashville's historical precipitation, going back to 1871. And I want to know 2 things. What's the probability that the expected rainfall in January is larger than July historically? And what's the probability that January rainfall exceeds July rainfall in a given year? So if you, let's say next year, do we expect? How will you have higher rainfall in January versus July? Okay, give that a try. I did the data import statement for you here, so you just have to specify the model. Now, sorry, I'm going to help you out a little bit here. Let's have a look at this stuff. So we'll do this part together. Let's do July rain. It's Nash precip dot July, and what did I say? January. Okay. And so let's have a look at this then. Okay, so rainfall data looks kind of like this. And so this is the tricky first part, right? You may have panicked when I told you you're just going to do this by hand on your own. And part of it was probably like, how do I go from this to specifying a model? Well, again, beginning at the beginning. What does my likelihood look like? And then what do my priors look like? Well, looking at the data, and rainfall data looks like this, right? It can't be negative rainfall, not even in Arizona. And it usually has a long tail out to the right. So which distributions do we look at? There are lots of common ways. Actually, Wikipedia's got a pretty handy reference of distributions. It doesn't do a good job of highlighting which ones are used all the time. Like I've never heard of a Champernowne distribution. You'll probably never use one in your life. There's a handful of sort of, PyMC's got like 30 or 40 of the main ones. So you can go in and look at PyMC3's documentation if you want to. If you look at, see, from PyMC3, import distributions, and then this one kind of gives you the list of all of them. but that can be a little intimidating too. So this one's pretty straightforward though. So it's continuous. Rainfall is a continuous value, but positive. So an easy one that I'm going to recommend is you take the logarithm of the rainfall and use a normal. So if we look at apply now it's skewed the other way, but you know, it's a good starting point, perhaps. You could also use a gamma distribution. Gamma distributions are nice. Right? So in real life, if you're presented with this problem, you would probably just go out and look at rainfall models and see what other people used. But gamma distributions are useful. See how they look? They can look bell-shaped, but they can also see this kind of skewy one here. That looks rainfall-y. Yeah. Yeah, let's do that one. So let's do this one together. With model as rainfall model. Call it whatever you want. Let's start with the likelihoods. So we'll call it January. I've already got that as the name of the data. Just call it Jan equals, we're going to import gamma from PyMC3, import gamma. Let's just look at gamma here. Gamma can be specified two different ways. It can be, the canonical way of doing it is it's got a shape and a scale parameter that determines this kind of weird shape, so alpha and beta. But often you want to, they're sort of hard to interpret, so you can actually alternatively, see how it says alternative parameters, use a mean and standard deviation, kind of like a normal. So we'll do that here. We'll use mu and SD, just like before. So we're going to call it mu equals, and we're going to end up calling this what, mu Jan. And SD, we're just going to call this sigma. We're going to assume that they have the same standard deviation at our peril. Observed equals Jan rain. And of course, we'll copy this and do July as well. Cool. Likelihoods are done. Priors. We need one for sigma. For those of you not familiar, if you're on Python 3 and you're in Jupyter, if you want a Greek character, you just go /sigma or / whatever the Greek letter is, and you hit tab, and it converts it over for you. So what did we use for variances before? I did a uniform one before. I did that weird half Cauchy thing. I don't know. Pick one. Uniform. Sigma. From 0 to 1,000. And then I'm going to go mu Jan. And this is just a mean, right? And this is, well, they want to be positive in this case, though, don't they? Let's go uniform again. From 0 to, I don't know, let's see, these rainfalls go as high, oh, that's log rainfall. Well, let's go up to, I don't know, 25. And we'll do the same thing for July. And then I'm going to add one of these differences again. I'll just call this D. Deterministic D. And it's going to be mu Jan minus mu July. And it breaks because June rain doesn't exist because I called it July rain. There we go. Model specified. Any questions about the model specification? I'll give you a second or two to catch up and I'll drink some coffee. It's exactly what I did before, just with slightly different problem. With rainfall model, samples equals fit, and something like on the order of 20,000 usually works, and then I'm going to draw 1,000 samples. Done. So now, oops. We do this plot posterior thing. Give it the set of samples, and then you just, so that it doesn't give us all of these variables, you can specify particular ones, and all I'm really interested in is D here, and samples with an S. Okay. And you can put a, well, don't need to. So, well, if you want to, you can, it's sometimes useful to put ref val equals 0, which is like the no difference thing. So our question was, what's the probability that rainfall was greater in January than July? In Nashville, you got about a 29% chance of having, of the expected value being larger based on historical data. How about for one particular so let's say next year, 2018, what's the probability of it being larger? So what we want to do then is, and I could have specified something in the model, but I can do this with the values afterwards. Let's see, what's the easiest way of doing this? It was easier before when I only had one Poisson parameter. So let's do things this way. We'll go, I'm going to go back and run the model again because that might be more intuitive running it this way. Let's call this January 2018. And I'm going to copy this line, except without the observed part, because these aren't things I've observed. But so one way I could have done this was to go back into my trace, pull out individual parameters from mu and sigma, and sampled from gammas, and then seen how many were larger than the other. I could have done that by hand. Here's an automated way of doing it. Well, here, I'll semi-automate it. I'll just do this. So this will draw my 2018 values. And then we'll do this. Jan minus July for July in zip. samples Gen 2018 samples. I'm sure there's a more efficient way of doing this, but this will work. Mm. 33% chance. Okay. So it's a little bit larger, not as extreme as the last time. But there's a little extra stochasticity here because it has two sources of uncertainty. One is the parametric uncertainty. We don't know what the means, although we have a pretty good idea because we have a lot of data. We don't exactly know what the means are for the 2 months over time. And then the stochastic part of drawing from a gamma distribution, right? So they're two slightly different values. Okay. All right. Last part of this section, yeah. Yes?
Okay, I guess I could get it on the video. You were just going so fast.
Okay. Do you want me to slow down? Anybody else need me to slow down a little bit? Maybe a couple people? A little bit. Too fast? Am I talking too fast, or am I going too fast through the examples? I'll try to slow down in general. Please ask one way to slow me down is to ask me a couple questions. So if you have questions, put up your yellow sticky. I will see it. Yours is up. Have you got a question?
Could you scroll down so we could see what you typed?
Sure. All right. If you want me to scroll back here? I will post all this stuff. So what I'll do after this is I will post all of these rendered with the examples and everything for sure. Mm-hmm. Is it PyMC related errors? Oh, so if you do from PyMC3 import gamma, does that error for you? Oops, this guy up here. One step that some people miss is if you're having a lot of errors, if you started this thing up before you did source activate stat PyCon, then you wouldn't have gotten all of the goodness that was installed. Anaconda installs a lot of this stuff for you, but certainly PyMC3 won't be installed automatically. So you have to do you have to install your virtual environment, and then you have to activate it. And then when you're all done today, you go source deactivate, and it'll go back to your original settings. So. Mm-hmm. Of this? Let me have a quick look at yours. So, oops.
This is a map to Dvorak, by the way, so let me know if I need to change that.
Oh. Yeah, pandas is. If you go up to the top.
The sheet sample.
Yes. Hopefully this gives some folks time to catch up. Yeah.
So, is that
Okay. Let's push on a little bit, and I will try to slow down. Please do interrupt me with questions if I lose you at any point, all right? We're not going to get through all of this, and that's fine. I'd rather you understand what I get to as opposed to me sprinting to the end. So, yes.
I'd agree with that. I don't know if not what everyone else thinks, but if you could go over that last example and explain what we're doing and why,
You bet.
that would really help me right now.
Yep.
I managed to implement it, but I don't really know what I did.
Sure. So the 3 steps, right? Specification, calculation, and model checking. I'm actually skipping the model checking step here, right? We've checked a model like this before, so that's okay. So are you okay conceptually with how I specified the model? How I chose things for the model? So the first step was to, have a peek at your data. And so I'm looking at this data here. And I'm saying that's sort of gamma distributed. I could have used, again, a log normal distribution, couple of other things. I'm trying to use something that's positive and continuous. Okay? Everybody good with me there? So I went in and instantiated a model, called it rainfall model, and what I started with was this gamma. I could have done it the other way around, started with the priors and done the likelihood afterwards. And so I created two gammas, one for January's rainfall. So its data is Jan rain, mu Jan, standard deviation sigma. And then another one exactly the same for July. And at least one person had the error where they cut and pasted and forgot to change Jan to Jul. And it looked like a mess, which we're happy about because we want, that's a good sign that you messed up and you want to go back and debug it. So now we got January and July, two gammas, two different distributions that overlap somewhat. Then we got to specify the priors, the things we don't know. There's two different mu's, and I did one standard deviation. I could have also said, well, maybe they're very differently dispersed, and so I could have two different sigmas if I want to. I could go sigma Jan and sigma July. Right? This is just a more general, more complicated model. No problem. I can do that if I want to. Uniform. Oh, did I do it again? See? It wasn't even cut and paste, just stupid me. All right. Okay, that works too. Then I wanted to look at the thing we're comparing. This stuff is kind of extra. These are conveniences. I could have just stopped here and gone back and pulled out the parameters that I need. This is kind of a convenience because it's doing this subtraction for me and getting samples of it for me. So, you know, it's just a deterministic node. It's just taking this and subtracting it from that. That's all. There's no extra unknowns or anything involved here. And then here are just draws from the posterior predictive. So I'm essentially taking this model and drawing a single value, an extra, I called it 2018. It could be anything. It could be just for, it could be a year in 1720 that I didn't observe. It's just some year that I don't know, didn't observe. And if it comes from this model, what's the expectation, or what do I think its value is going to be? And so now I'm done, and I run the model. And someone started asking me about why 20,000, all that. These are, I'm trying to make this a black box. That's just a good long enough value for us to get a good estimate is all we really need to know right now. Additional questions about this? Mm-hmm. Oh, it's not. I'm using it later. So I use it after I'm done. I'm interested in that value. I'm interested in that value. I want its distribution. So here's where I use it. At the end, I see, well, what's the distribution of that difference, right? And how different from 0 is it? So there's a 91% chance that it's greater than 0. On average, 28% larger, or 0.28, sorry, 0.28 larger, not 28%. Does that help you?
Yeah, that was exactly.
Okay. Please stop me if I don't want to lose people in this. That would be failure. Okay. So now we're going to switch to another type of data. Binary outcomes. As I said, these are pretty common yes and no things, obviously not continuously distributed. So first thing that should come to mind, oh, we're probably not using normal distributions anymore, at least not for data likelihoods. We get binary outcomes a lot. You should never, ever create them. Never take a continuous variable and make it binary. You are throwing information away if you do that. Okay? You may be interested in some threshold value, and you can deal with that after your analysis. But anytime you discretize something that's continuous or dichotomize something, all that money you spent on collecting data, you're essentially just taking some of it and throwing it in the trash. Always build a model for the data that it was originally collected for. So, if you do have binary data, yes.
But sometimes it's useful to take continuous data and say, I believe it falls in these categories, right? Which isn't the same as going binary, but it's somewhere on that continuum.
You can do stuff like that afterwards, after you've done your analysis. So again, this is something I get a lot with doctors, right? They like to diagnose, right? Sick and not sick. You know, if your BMI is greater than 30, you're obese, otherwise you're not. Well, come on. Some things are true step functions where you cross a line and, you know, bad things happen, but generally, stuff like that, it's a continuum. And so you can fit the continuous model and use all the information and then say what happens at BMI 30 or what happens at some other arbitrary threshold. So that sort of that you can do that decision making, but do it afterwards, and then you're not throwing information away. So that's the difference. So data that is dichotomous, the distribution we're interested in here is the simplest distribution in statistics. It's called the Bernoulli distribution. And it describes the outcome of a single coin flip, essentially. All right? It has one parameter, p. It's the probability of the event occurring, where the event is one of the two outcomes, true or heads or something like that, die or something like that, right? And then x is either 0 or 1. There's only two possible values, 0 or 1. So you can see what happens here. If x is 1, this becomes 0 and it goes away, and p. If x is 0, that one goes away because that's 0. Anything to the power of 0 is 1. It gets multiplied out. And it's 1 minus. So it's either p or 1 minus p, right? Probability of it occurring or the probability of it not occurring, which is just the complement. You often see sums of Bernoulli events, which is known as binomial data. So again, sorry for always using clinical example. Oh, let's use a baseball example. If you're a sabermetrician, somebody hits the ball 30 times out of 100 at-bats. That's essentially, 100 coin flips, 30 of which came up heads, same idea. And so that data would be binomial. And the binomial distribution is just the sum of n Bernoullis. So if you had 10 coin flips and you want to assess the probability of heads, you'd have n equals 10. P is the probability of heads, and that would be the model that you use. And you see they're very similar. They're exactly the same, except you just if you put 1 here instead of n, it actually reduces to that. So it's just a special case. Okay, so this is the distribution we're interested in here. Yeah. There's a whole raft of distributions like I showed you, but in reality, there's like 15 that you use kind of every day. And binomials definitely, it's probably the second most important distribution in statistics after the normal. All right, my data that I'm going to use for this one is a biomedical one. It's a set of 671 infants from the Duke University Medical Center. And these are very low birth weight infants. And if you're born prematurely, there are all sorts of negative health consequences associated with it. And one of them, the outcome that we're going to study here, is IVH, intraventricular hemorrhaging. So the ventricles in your brain hold essentially your spinal fluid, and you can get bleeding in there. So the hemorrhaging means that it bleeds, and it's obviously not something that you want to happen. And so it's a negative outcome, and we're interested in things that are potentially associated with it. So this is this data set here, VLBW. So this is actual real data. And it's got a whole bunch of stuff here. How long they stayed at the hospital, a bunch of labs, race. The one we're going to be interested in here is birth weight. And there's another variable, another binary variable called presence of a pneumothorax. And a pneumothorax is essentially a collapsed lung, which can also happen. And we're going to see if any of these things can predict whether or not you get intraventricular hemorrhaging in low birth weight infants. Okay. So what we're going to do is see if there's a difference, if there is a difference between infants with and without this collapsed lung. And so we can do our pandas magic, pandas crosstab. So these are, so in some patients, there's no pneumothorax, well, most of them, no pneumothorax and no IVH. So they're both kind of rare events, even if you're sick, even if you're premature, I should say. Some of them have both, and then, you know, all possible combinations. And we're going to combine definite and possible into one. So things become a little more complicated when you have more than two categories. It's a different distribution. So we're going to combine definite and possible. So that's what this step is doing here. So I'm going to create two variables, one called IVH, yes or no, and the other is the pneumothorax. I'm just calling that X. Okay. We already know our likelihood. It's going to be Bernoulli. So every individual, every baby in the data set is you know, the coin flip, essentially. And so we are interested in a prior distribution for the probability of this event, of this unfortunate event, of the IVH. What do we use? Well, so we think about P. P is a probability. It has to occur between 0 and 1, right? So it's more heavily constrained. It's not just positively constrained, but you can't have probabilities greater than 1. You can't have probabilities less than 0. Well, one of the cool distributions in statistics is the beta distribution. And the beta distribution is defined on the unit interval, as they call it. And it's got two parameters, alpha and beta, similar to the canonical gamma distribution. And you can see you can make it do lots of things. The more parameters a distribution has, the more weird stuff it can do, the more flexible it is. Right? So you can, you know, it can be slopey on one side. It can be almost normal looking when it's in the middle. It can be boat-shaped or bathtub-shaped. The one we're interested in here sometimes here is the flat one. So alpha 1, beta 1 actually is a uniform distribution. So this is saying equal probability of all values, for example. So we're going to use the beta as the prior distribution for the Bernoulli. Okay? So we specified our model, essentially. We got two Bernoullis, each of which will have a different P, a different probability of getting IVH. And the unknown value is that probability. And we're going to put beta priors on them, okay? Everybody follow? So let's dive right in. Priors. I'm changing my notation slightly just to give you an idea of what you can do. Instead of having P pneumothorax, P no pneumothorax, I'm just going to say P shape equals 2. So I'm going to have two of them, and I'll just index them out as I need them. Just a little bit more economical. And then down here, here's the Bernoulli likelihood. I've got to import it first. Don't forget. As I did with beta. I must have imported beta before somewhere. Oh, to show this, I think. Anyway, and then I'm going to use cool NumPy / pandas indexing for this. So X is 0 or 1, pneumothorax or no pneumothorax, right? So it will index out the 0th P for the no pneumothorax group and the index 1 P for the pneumothorax, right? So I don't have to have two separate likelihoods specified. Everybody clear about what this is doing? Okay. So it's going to. So P here is a vector of size 2. I'll do a dummy example for you here. Let's call it foo equals -5 and 7, for example. Let's make it a NumPy array. And then foo index is, let's say, 0, 0, 1, 1, 1, 0, 1, 0, 1. So if I go foo ind, see, so it pulls out the appropriate value. Pneumothorax, pneumothorax, no pneumothorax, no pneumothorax. So it's pulling the appropriate P for the appropriate patient. Does that make sense? just Python. It's just plain Python indexing. That's nothing too magical. Okay. So it is, and then observed is the IVH variable. Oops, the IVH variable. Sure can. Beta is the prior for P. So remember what a beta 1,1 looks like this. So we're saying, a priori, we have no idea what this is. Obviously, well, we do, right? It's a rare disease. It's a rare thing. So maybe I should have chosen that one as my prior. It probably won't matter in this case, but.
And then you're sampling P from the beta and then using that on the probability.
That's what's going to happen internally. All this is defining an information state. This is what we know about P before we did our experiment. It could be anything. The likelihood is this Bernoulli. And remember, Bayes' formula is our estimator. So if we combine that prior with the information in this data, I should get, that's what Bayes' rule tells us, I should now get what we know about P given my data. So yeah, don't try to think too hard about, oh, is this sampling from that? It's not, we're doing sampling to approximate our posterior, but really we're integrating. We're multiplying probability distributions together and integrating them is all we're doing.
I'm trying to understand what beta actually gets you. You're saying alpha, and if you set them equal, then you get a uniform distribution?
If you set them both to not just equal, but both value of 1. So they're equal, actually they're equal here and they're equal here, but they're different values. That's 5 and 5, that's 0.5 and 0.5. They're just different parameterizations. They're hard to interpret what alpha and beta are. They're both kind of shape and scale parameters. So they're not as easy to interpret as mean and variance. Those are very easy for us to get our heads around. All you're really looking for is a shape that describes your uncertainty. I do this all the time with folks who aren't statisticians. You know, does this describe what you think the value of this is before you go ahead and run this trial, or is it that? So it doesn't matter if nobody cares if it's alpha is 2 and 3 or whatever. It's, does this represent my knowledge? This just happens to be the values that give you that. So don't overthink the particular values. But this is an important one. When it's 1 and 1, it means it's uniform. That's kind of a special case that's important. If you really want an interpretation, alpha is kind of the prior number of events, and beta is kind of the prior number of non-events. Right? So this is 50-50 with 5. If it was alpha equals 5,000, beta equals 5,000, it would be like a little stick over 0.5. This is 1 success and 3 failures, and so you see it's kind of tilted towards 0, but not dramatically. That's if you want an intuition about it. You seem perplexed by that.
This is what we know before we do our thing, or what we think we know.
Could be nothing. I've claimed we know nothing. That's ignorance. This last one over here is ignorance. Yeah. Any other questions? Yeah, priors, yeah, it takes a while to get your head around priors. But that's what you're trying to do is ascribe a state of knowledge. And for something like a clinical trial, you'd almost always want flat priors because the FDA doesn't care what you think your drug is doing, right? The FDA wants to know, does your data in your experiment reflect it? Whereas if I'm an epidemiologist and I want to know something about stopping an outbreak that's going on now, I want to use all the prior information that I know to help me make a decision about whether to vaccinate all the children under 5 years old, right? That's when you want prior information. Or you just want the best. The goal at the end of the day is to get the right answer most of the time. And that involves bringing all information available to bear on the problem. And if that's prior information, great. If it's data from an experiment that you're doing, that's good too.
Curious about the FDA, whether they, in your opinion, have they embraced Bayesian?
They have absolutely embraced Bayesian, yeah.
Even for very rare events like 1 in 1,000 kind of chance, the prior, if you have enough number of
That's absolutely, yeah. So, well, it depends on amount of information, right? So if I did give this an alpha, hey, let's do it. I'm not just going to describe it. Let's try it. So let's hold off the questions for a second. I'm going to run the model as it is. Okay, here are the P's. So P for pneumothorax is 0.32, and P for no pneumothorax is 0.12. So it's saying 12% chance with no pneumothorax, 32% chance with pneumothorax. And they're definitely bigger. So there is an effect of the pneumothorax. So let's go back and say, so the claim here, if you didn't hear the question, sorry, I've been crappy about repeating questions. Sorry about that for people watching this on video. The claim over here is that even if we gave it a misspecified prior, if you've got enough data, it's not a big deal, and that's generally pretty true. So if I go in and I go P, I don't know, let's give them like 5.1 or whatever. Okay, so let's remember what the means were down here, 0.12 and 0.32. Pretty close, right? So turning it from flat to even basically that on the other, basically this, but with a 5 rather than 3, didn't do very much. Let's now specify a beta 50,000, 50,000, beta 50,000, 50,000 prior. Basically just like a little spike at 0.5. You can totally, yeah, you can influence it. But what we were saying, 50,000, 50,000 is basically a prior sample size of 1 million. And my data set here is, what, 130 or something like that. So, yeah. So if you give it more prior information than experimental information, you will overwhelm the prior. And so, yeah, this is cheating, but you can't hide that from anybody, right? You got to say somewhere in your paper that you used a beta 50,000, 50,000 prior, and somebody will go, oh, excuse me, right? Yeah. Yeah. Oh, no, they don't. No, no, this is P for the kids with the pneumothorax and P with the kids without the pneumothorax. They're not associated with one another. It's not the probability of not getting IVH versus the probability of getting IVH. It's, it's batting average of one team versus the batting average of another team. Correct. Yeah. The question there was, did the P's not have to add up to 1? And no, because they're two different probabilities. They're for two different populations of kids, essentially. Better change this before I commit this, right? Okay. Any other questions about that? Hey, we've reached the end of that piece. Yeah. That's the big advantage of Bayes, is that you can do this turning the crank on the Bayesian machine. So you can take the posterior from one analysis and then use it as the prior for the next time you do an analysis, if it's studying the same phenomenon. And you can absolutely do that. There are technical challenges to doing that. Sometimes nice thing about this beta Bernoulli thing is that they're known as conjugate likelihoods and priors. And what conjugate means is that if you have a beta likelihood and a binomial or a Bernoulli, a beta prior and a binomial or Bernoulli likelihood, the posterior will also be beta distributed. And so then you could take that beta and immediately insert it in as a prior. But that's not always the case. So before, when I had a normal likelihood and a half Cauchy, something or other, and a uniform mean, the posterior doesn't have any particular form. And so then what you'd have to do is somehow summarize the posterior and then take that summarized form. So you'd lose a little bit of information in practice doing it. in theory, there's nothing preventing you from taking that distribution and plugging it in as the prior. Okay. So we have like 20 minutes or so left, which isn't much. Let me see if we can do anything with regression in that time. Yeah, I think we can. So regression models essentially generalize what we saw before, comparing two groups. When we were comparing two groups, it was basically just two input values, pneumothorax or not, right? Placebo, treatment. Sometimes we have a continuous variable or several continuous variables as an input, or several binary variables as an input. For example, how do different medical interventions influence the incidence of disease? How does baseball players' performances function, change as a function of age, which is continuous? This was a fun example that I found, how test scores are correlated with tissue LSD concentration. So here's a nice little data set. And it's a paper. Note the year, 1968, right? Correlation of performance of test scores with tissue concentrations of lysergic acid diethylamide in human subjects. So they gave them LSD and made them take tests. And surprise, surprise. So you pull this in. They go down as you get more drugs, right? Although it's funny because I saw an article in The Guardian like just the other day when I was putting this together. Cary Grant, how 100 acid trips in Tinseltown changed my life. So it depends on what you're getting tested on, I suppose. If it was like songwriting or creative writing or something like that, maybe it would go the other way. But this probably wasn't that. So let's fit a model to this, right? We want to fit a model to this, and so we would want to draw. We'd draw a line kind of like this. And so what's the criterion for drawing that line? If I put my arm here, why am I putting my arm here and not like there? What am I trying to do? Minimize, the difference between the line. Put the line as close to all the points as you can, right? We've all probably taken regression courses, I'm just seeing. So we want to characterize the relationship between x and y, and really, generally speaking, what we're doing is generating conditional expectations. So we had conditional expectations before. There we go. Before, but they were just 2 points, treatment and control. So we want y given x, where x could be, any age or something like that, or concentrations of LSD. And we get an expected value of the outcome given x. Okay? If it was Bernoulli, if it's binary outcome, it's the probability of, a pneumothorax as a function of birth weight, for example. That's one of the examples later on. So in general, this function of x can be anything. It could be a weird non-parametric, non-linear thing. For regression models, they tend to be linear combinations, right? So we're multiplying coefficients by each of the predictor values. So you can easily generalize this to more than one variable, and it's just the sum of those, and then a baseline value or an intercept, right? We've seen this probably in a stats class before. And there's two important linear regression assumptions. One is that the errors are normal, so the differences between the line and the points are normally distributed. And what's called homoscedasticity, which means that the variability doesn't change along that line. It's not more variable at one end versus the other. If that's not true, regular linear regression is not for you. You've got to do something slightly more general. So it doesn't take much, actually, to fit one of these regression models without any fancy PyMC3 magic. You can just use straight-up optimization. What you need is a criterion for choosing the values of those beta parameters, right? And our criterion was as close as possible to the data. Well, this is sort of what this is saying. It's the data minus the prediction from the model, and I'm squaring it. I don't have to square it. I've got to do something, though, because positive and negative differences will cancel each other out, so you can't just add them up, right? I'm going to square it. Square it does two things. It prevents these cancellation that I just talked about, but also more strongly penalizes large deviations. So the difference is squared. It makes it bigger. So this is essentially a value judgment on our line, right? We don't like big deviations, only little ones, okay? And we're going to minimize this. We want this to be as small as possible. And this is just optimization, right? So we can do this by hand, more or less. So here's this function as a lambda expression in Python. So this is just that. Yes? That's the next. If I scroll down, we'll see that. That's somebody else's value judgment. These are just criteria. All right, and so I can put in, arbitrary values. 0, beta naught equals 0, beta 1 equals 1, and that's what that sum of squares is. And if I change it very slightly, make it 0.7, I'll get a slightly worse value. So I guess I got to go in the other direction, that kind of thing. So we can go into SciPy and pull out fmin, which is just the Nelder-Mead optimization. There's many ways of optimizing. We'll just use this one as a black box again. We'll give it x and y, which are the values from the LSD data set, and we just run fmin. And all it's doing is hill climbing. It's or valley descending, opposite of hill climbing. It's minimizing that value. And then, lo and behold, that's our line. And this is the one where these, and it's perpendicular distances. Sometimes people think it's that value. It's not. It's these ones that they're trying to minimize. Okay. So you don't need to be Bayesian or do sampling or anything to do this. You can just use optimization if you want to. Alternative loss functions. Here we go. What if we don't want to punish big values? Well, we can use the absolute value. So we always do want to get rid of that cancellation effect, but we might not want to whack the ones that are way out of line. And in this case, there weren't any big outliers, so I think the line looks pretty much the same. We don't have time to do the example that I was going to do. This was the exercise here, is add one more extreme, an extreme observation like out here. And then fit them two different ways. And what ends up happening is that the sums of squared errors tends to get drawn out. The line starts tilting this way just a little bit. It's only 1 point, so it's not super influential, but just a little bit, whereas absolute value pretty much keeps that line the way it is because it's proportionally allocated to that. It's sometimes known as robust regression, that you never want to throw out outliers. You want to model outliers, right? Much better way of doing it. And that's a way of doing that. We're expecting that one. Or we just don't want that extreme value to influence things too much. Right? Okay. We're not restricted to straight line models. So we can expand this and use what's called a polynomial regression. So all I've done here is added an additional term that's x squared. And that allows things to be nonlinear, it allows things to be quadratic. So if I run this one, it actually looks, there's a very gentle, this isn't a good example for this because it essentially is linear. Not many subtle things are happening with the LSD effect on your tests. But it's a very slight curve. And the nice thing about this is that it's still a linear model. Even though the curve is not a straight line, it's still linear, and it's still a linear combination of those parameters. You still take a vector of betas and a vector of x's and x squared and multiply them together. And that's still a linear model. So don't confuse those together. But here's one that's slightly more curved, and so this one would have that probably a better place to use the polynomial value. Okay. So in the 10 minutes left, I'm just going to show you how to do this Bayesianly, and then we'll wrap it up. So the same thing here. We're going to do a Bayesian approach to regression. And the nice thing about this is that we're also going to be able to give ourselves, not only, the line isn't the only important thing, but also the uncertainty in that line, just like uncertainty in our predictions about what the probability of IVH is. And so we're going to do the same thing here. So we need priors. So what do we need priors on here? Well, we need priors on those betas, right? Beta naught and beta 1, or however many betas we have. And then we also need a prior on the variance, right? So the sums, how the expected value of the differences between the points and the line. So regression parameters and variance. And so I'm just going to use normal, mean 0 with standard deviation of 100, like really wide, almost flat. Could have used uniform again. And then that half Cauchy thing, maybe. I could also use uniform here. This is what's known as the process uncertainty. Again, the difference between the line and the points. That's all. Okay. So those are our priors. Oh, this is what a half Cauchy. Ooh, that's not what a half Cauchy looks like. What's wrong with that? Oh, okay. I ran it again and it worked. That's what half Cauchy looks like. So so here are my priors. So I'm going to give them user-friendly names: intercept, slope. All right, sigma isn't user-friendly, but never mind. Okay, it's just what I said I would do. And then likelihood, this is a linear regression, so the errors are normal. That was one of the assumptions, in fact, of this, is that the errors are normal. So you don't even have to make any choices here. If you're not choosing normal here, you're not doing ordinary linear regression. So normal, score. Your scores are normal, the test scores. Mean of mu and standard deviation of sigma, where mu is the sum of the intercept and the slope times x, which is the dose of LSD. Notice here I didn't put deterministic around it as a technical note. And that's because I'm not, well, I might be interested in mu. This is just nicer to look at, but also I just wasn't planning on looking at mu. So it's not going to keep track of mu at every iteration of the model fitting. It's just going to stick it in here. So it's sort of an intermediate value. I'm mostly interested in the beta parameters. So there he is. We're done. And this time, just for variety, I'm not going to use variational inference. So instead of fit, I'm going to use sample. Sample does Markov chain Monte Carlo, which is a as the name implies, a Monte Carlo-based approach that takes dependent samples and does the same thing. It gives us an approximate posterior, sample from an approximate posterior. Okay, it's done. Could have easily have used fit there, just using some variety. And so the slope here is about -9. So it's saying for every unit increase in dose of LSD, you can expect to lose 9 points off your test score. Show it to your kids. Say, look what happens. This is your brain on drugs. Few minutes. And then same thing with checking model. So here's a good example for checking model fit. It might be even clearer than the one I showed you before. So what I'm going to do here is I had 7, or looked like about 7 points there. What I'm going to do is sample for each of those 7 actual data points. I'm going to sample a whole bunch, simulate a whole bunch from my model, and see where that simulated data lies relative to the observed data. See how close they get. And I could do this by hand, but there's a nice little utility function in PyMC called sample PPC, where PPC stands for posterior predictive check. This is exactly, this equation is the same as I showed you on the other one. So recall, it's a function of both your posterior distribution and then the sampling distribution of your data. So 2 component, it's usually more variable because it includes uncertainty about the parameter and then stochastic random sampling stuff. So I'm going to do sample PPC for 100, and so, or 1,000, excuse me. It's going to draw 1,000 data points for each data point that I use to fit this model. And this just proves it. So there were 7 data points, so there's 1,000 for every one. So we'll have a distribution for every one. And so I'm going to plot each of them. That's what we get. And you can see this is fit model, goodness of fit. It is a good fit. Or, sorry, to be technical, there's no evidence of lack of fit. That doesn't prove anything. It's only 7 points. But we're happy that these red lines, which is the true data, are believable draws from these distributions. So it's saying that, yes, my model could have generated this data. Yes, the relationship between LSD and test scores is approximately linear. Right? If we'd be worried if the line was out here. It's 4:37. So yeah, we didn't get to, obviously, well, we didn't get to a lot of this stuff and missing data, and that's fine. But yeah, I didn't want to blow through this any faster than I did. I left a few minutes for questions, so maybe let's take like 5 minutes if you've got maybe big picture questions about Bayes or applied Bayes. Yeah.
So you kind of got it, but not quite.
Right.
What references or what to study or where to
Yep, that's a good one. So at the bottom of each of these notebooks, I do have what I would call specific references on specific things. So these are, regression books. This book called Data Analysis Using Regression in Multi-Level Hierarchical Models by Andrew Gelman and Jennifer Hill is a really great applied regression book if you do a lot of that kind of stuff, and it's Bayesian. A really good site to get an intuition for this stuff is Bayesian Methods for Hackers. So this is kind of cool. It's essentially an open source GitHub repository that is a textbook. So it was like a community developed textbook on this stuff, and it gives you really intuitive taste of Bayesian inference, also using Python and also using PyMC. So that I would recommend this. It's very readable. It's very non-technical in the math sense, but technical in the computation sense. So it's probably good for this audience. That's a good one. There's a bunch of good intro to Bayes books, but I would start with this. Any of Andrew Gelman's books are very good. He's a social scientist, and so he's in the stats department at Columbia, but he talks in English. So, yeah. Any other questions? Yeah.
Does the PyMC package, is it built on other things like SciPy, or have you basically rewritten a lot of the...
I started PyMC 3 when I was a postdoc, like in 2003, and it was pure Python. And then it was, a lot of these methods like MCMC are really, really slow because it's got to evaluate the complete model likelihood at every iteration. And so we used Fortran extensions with F2Py for PyMC 2. And then the more recent one, PyMC 3, which you're using now, is based on Theano, which is an expression evaluation library similar to TensorFlow that's used for deep learning and stuff. And so it builds this big graph and evaluates it. And all these modern methods for fitting Bayesian models like variational inference and the newer types of MCMC all use gradient information to accelerate the approximation. And so Theano does automatic differentiation. And so it will, so that's why we switched over to that. So the answer to your question is, yeah, it's basically all Theano. And we try to hide as much of the Theano from you as possible because it's not easy to use Theano straight, It's like drinking fire whiskey. cut it with something. Any other questions?
And tell me, I mean, like 3 cases where the Bayesian underperforms the frequent distributions.
Outperforms?
No, I mean, underperforms.
What do you mean by underperform?
Because, like everybody is going towards, like Bayesian.
Uh-huh.
So, I mean, like,
What are examples?
to the like old statistics models.
Oh, what will happen to them? I don't think they'll go anywhere. You know, I became a Bayes. I never took any Bayes when I was in college. I came about it very pragmatically, and it had to do more with I had big models to build, and I had no choice really. I couldn't fit them using maximum likelihood and frequentist methods, and so I had to adopt Bayes. So all this philosophical nicety that I was talking about had really nothing to do with my own journey towards using Bayes. It was more Bayesian. The other feature of Bayes that I didn't really talk about is that it looks very simple, but it's actually a bunch of simple building blocks that can be used to build very complicated models. And so big, hierarchical, multi-parameter models are much easier to fit with Bayes. And there's some that, you know, you can do benchmarks and you can compare things for performance characteristics, but there are some models that you simply can't fit using non-Bayesian methods. And so that's kind of more the difference. You can make Bayesian models and frequentist models look the same if you tweak them the right way, show some sort of equivalence, but they're not equivalent because they're using probability in 2 different ways and everything, so it's hard. Yeah.
A big part of our organization has been using the frequentist approach, and all the business people are familiar with the t-tests, t-scores, etc. And now we are trying, as a small group, we are trying to shift to the Bayesian approach. If you're in a meeting with a few business people and it comes up, hey, why are you doing this instead of the method that we have been using for years, and if we had 1 minute to respond, what would you say?
Oh, well, I gave you the criterion at the beginning. They're easier to interpret. They're more direct questions about the uncertainties of interest, the question of interest. They scale better to bigger models, and they're, I think that's the biggest, particularly to a non-statistical audience. They're easier to interpret. So people think they know how to interpret a p-value, but mostly they don't. In fact, most people don't interpret confidence intervals the right way. So I usually sell them on that. And then just showing the types of models that you could fit with Bayes that you just can't even dream of otherwise. I'm a big fan of, convincing them by showing them as opposed to trying to explain it or sell them. You just show them this big analysis. Oh, and by the way, it's done with Bayes. That's almost secondary then.
Between frequentist and Bayesian models, do you observe significant difference of means between a priori and posterior, or is it more about the spread and the shape?
It can be entirely different, again, because you're involving priors. The priors tend to shrink things. So have you ever done lasso regression or ridge regression? That's the equivalent of putting priors on the regression parameters, and it shrinks them towards 0. In fact, they're exactly equivalent. So yeah, the priors will influence them. But again, the probabilities that you get from a frequentist analysis are the probabilities of the data of what you would observe in the data if you repeated your experiment 1 million times or an infinite number of times. The probabilities you get here are the state of information about parameters. So it's really apples and oranges comparing them. You can, like I said, you can rig analyses to get frequentist confidence intervals the same width as Bayesian credible intervals, but they're addressing 2 different things. One is addressing the position of the mean, and the other is addressing the endpoints and how often they will include the true mean. I should probably end it there. I'm going to do 2 things. Thank you for coming and staying, and B, sorry for the technical difficulties. I should have anticipated these better, and sorry if I didn't go slowly enough. But I hope you learned something out of this. And I'm not getting rid of the repository. I'm going to leave it there. Feel free to go through the rest of it and email me with questions if you like. And good luck. Thanks.